My name is Keith Basil. I am co-presenting today with Sean Cohen and Tushar Katarki. This talk is about deterministic capacity planning with OpenStack. So we'll just jump right in the essence of time. So this is a picture that's been floating around the internet, and I think it summarizes some things that we're going to see here. So the big question is, who is this guy and why do we care? We care about this guy as an OpenStack cloud operator. So we'll get to a little bit more detail on who this guy is. So the quick agenda here is to maybe do a 5-minute review on OpenStack as an elastic cloud infrastructure. We're going to talk about determinism, and then we're going to go through each of the components that make up OpenStack in terms of compute, storage, and networking. And then we're going to show from an architectural point of view how you put it all together. All right? So a little bit about me. You guys can look up that later. I ride dirt bikes in Virginia. Sean is a jazz guy, and Tushar is a world traveler. Not really important for the context here, but we put it up there anyway. So jumping right in. Hello, I am your elastic cloud. So this is OpenStack. We're going to spend about 5 minutes here to talk about OpenStack. As you guys know, it's open source software, has a very large community, over 10,000 members, provides a framework for what we call the elastic cloud. It's very different from what we call enterprise virtualization, which we'll talk about in a second. And this benefits from best practices that you see in public clouds in terms of making sure that the resources are consistent within the cloud. So you've seen this pets versus cattle thing, I'm sure, several times. So it's very important to understand that the elastic cloud is not the same as enterprise virtualization. So the elastic cloud, Amazon, Google, OpenStack-based clouds are very different from, let's say, Red Hat Enterprise Virtualization and VMware as enterprise virtualization. So with the elastic cloud, applications are they expect the infrastructure to fail, okay? So they're smaller stateless VMs kind of built in a layered fashion. And the thing about the elastic cloud is that you as a consumer of that cloud, you basically have a menu of predetermined options that you can use to build your applications, okay? And the life cycle of those VMs are very quick. They are short-lived at most times. And the beautiful thing about the elastic cloud is that if a VM dies or a compute node dies, you don't really care, right? You treat it like cattle. You take it out back and you shoot it, okay? Whereas on the enterprise side, the workloads are very different. These things are like traditional enterprise workloads like big Oracle databases, Microsoft SQL Server, Exchange, these guys that have, heavy resource requirements where if you need more, you just make the virtual machine bigger. You add more RAM, you add more vCPU, et cetera. And those things tend to stay up for years, and they don't have any notion of how to deal with failure. If the compute node that virtual machine is running on fails, the application just crashes, right? So this is scale up. So if your machine has to stay running, and if it goes down, everybody treats it like we got to get Bob back up, then that's what we call a pet model, where you have pets where you actually take care of the pet, you take it to the vet, you nurse it back to health, and you have an emotional attachment to that particular virtual machine, all right? So it's fundamental philosophical difference here. Okay, so looking at the resources, this kind of further drives home the point. So the difference between the resources, in the enterprise virtualization case here, you as a consumer of that cloud infrastructure, you determine what the virtual machine looks like. So you say, hey, I want a virtual machine with 6 virtual CPUs, 4 gigs of RAM, and 120 gigs disk. Okay, you specify that virtual machine. On the OpenStack side or the elastic cloud side, you don't have the power to specify that. You basically pick from that menu and say, hey, give me an M1 small, whatever that means, right? And then you use that as a fundamental building block to build your applications. So you can't go to Amazon and say, I want this custom virtual machine instance, right? You have to just use what they give you in terms of instances. So that's a fundamental difference between the two. Okay, so since we're talking about OpenStack, I'm going to go through OpenStack to level set everybody in the room in about 2 minutes, all right? Maybe less than 2 minutes, but. So here you are as a consumer of OpenStack, and you say, OpenStack, I want an M1 medium virtual machine. So that's a machine of a certain capacity, certain disk, certain RAM, et cetera. First thing the OpenStack says is, okay, do I know you? This request came in, but I don't know if it's authorized. So it calls Keystone to verify that you're actually authorized to pull that data or to make that request, So Keystone says, hey, everything looks good, creates what's called a token that gets passed around to the services. And now Nova, since you requested a virtual machine, Nova gets involved and says, hey, papers are good, I got the request, let's get to work. Okay, so Nova then says, hey, I need to find a compute node to put this virtual machine on. So there's some scheduling that happens in that process. He finds a node that's fairly empty based on some filter scheduler rules and says, hey, you're going to be the compute node that I'm going to render this virtual machine on. And then Nova says, hey, Neutron, I need to have some networking bits that go along with this virtual machine. So Neutron, give me a network with all the trimmings. And then Neutron says, here's your IP address, here's your default route, here are your firewall settings in terms of a security group. Now notice the machine hasn't been created yet. We're just kind of gathering data as the token gets passed around the ring. Okay? So Cinder, the guy requested M1 medium, but I think he wanted to have a block storage volume attached to this as well. So I need to get that volume. Can you provide that for me? Indeed I do. Don't forget to mount it. It's part of the VM. Again, nothing's been rendered yet. Everything's just kind of being collected. And then finally, in the request, the guy said, hey, I want to run a Rails 6.4 image on this virtual machine. So Glance, which is a component in OpenStack that catalogs images, Glance says, hey, here is the location, the URI for that image. Nova, you can now pull that down to the compute node and start to put everything together. So it's rendering time. So we have all the data that we need to build this. So Nova then renders that instance on the compute node, boots up the VM, and then we have a running virtual machine with all those trimmings attached to it. And you as a tenant says, thank you, OpenStack, I have my virtual machine. All right? So as a cloud operator, this is your mission, okay? So I've got two quotes here from DevOps guys. The top one is a guy who wrote a book called What is DevOps? And it's all about, as we showed earlier, about having applications become reliable on top of unreliable infrastructure, right? So applications are what matters to my friend Mark. We're trying to get applications deployed faster and faster. This is the business case for running on top of the Elastic Cloud. This is your problem space as a cloud operator. You need to make your tenants happy toward these goals, okay? So back to this guy. All right, our goal as a cloud operator is to keep this guy in play. These are your DevOps guys who are highly skilled, who just look at infrastructure as code. They're riding the OpenStack unicorn into the sunset, into glory. So just keep this in mind in terms of what you're building for, okay? If these guys want to have X number of VMs, consistency, performance, whatever, this is your ideal tenant. So with that, we'll bring up Sean to talk about determinism in the infrastructure.
Thank you, Keith. Yes. So to those of you who attended Jim Whitehurst's keynote on Monday, Jim actually gave the analogy of cloud infrastructure to cities infrastructure. And we'll talk about that in a second, but one of the things that we've seen is the perception of infinite cloud, especially from the user perspective. All of us are using cloud services today, even for our emails. We don't expect that the capacity of our email attachments will go out, right? We don't give it a file at all. We expect that the cloud provider will deal with it, right? This is what cloud elasticity is all about. Newsflash, there is such thing as an infinite scale. Every virtual machine at the end of the day is connected to a physical device, and that physical devices are limited. It's our job to do better planning, to make use and build this infrastructure, right? And we look at capacity planning in the cloud, every provider has its limits. Now, it doesn't matter how big the provider is, it has limits. However, adding the word cloud doesn't simply squeeze the limit button. It does not eliminate the issue, right? So elasticity doesn't solve the problem. It's part of the problem. And believe it or not, it's part of your problem, right? This is why we have this session today, because this is the part of things you have to plan out for. And we're sitting here in San Francisco, and going back to the analogy of cloud infrastructure in cities, I don't know how many of you know that this week exactly, 108 years ago, this city had actually survived one of the largest natural disaster happened, with San Francisco known earthquake and fire that actually devastated the city. The city had to rebuild almost from scratch with no time. If you need to build your infrastructure in no time, you have to have infrastructure codes, right? And this is what we saw happening. So we had to build this new commodity rules to allow this is the certain bricks you will allow to use to build your new houses, because we have to do it. In cloud infrastructure, we have the same problem. For us to be able to scale up fast, we have to have these building blocks, right? This is why we need to build in code. And this is actually a takeaway from infrastructure as a code that is a known DevOps statement, right? So why history matters in cloud computing? Because we have to track our history. If I'm a cloud provider and I have spikes and valleys over time, I need to record them. If I'm approaching holiday season and I'm a retail online service provider, I need to be able to deal with the spike. Because what it means, I need to allocate elastically much more resources to support that spike. If you don't do it in advance, if you don't prepare for that spike in advance, you lose your business. Simple as that, right? So this is why cloud performance monitoring is a big piece of it. We have to record our history when it comes to cloud computing resources. And we look at the implicit contract between the operator that Keith mentioned, right? So that's our hero guy. And to the tenants that are actually serving. Another thing comes into play, and I mentioned that your email attachments, for example, right? You don't expect that the cloud provider will run out of space, but what we have in the middle is actually what we call the SLA, the service level agreement. I'm the cloud provider. I'm offering you to buy that capacity, right? Compute, network, storage. And you can buy it in chunk, you can buy it on demand, et cetera, but I'm actually bound to provide you this elasticity going forward. In order for me to do that, over subscription, et cetera, I have to take all those things into consideration. And where we look at deterministic capacity planning is actually the ability to measure and predict what will be the increase size in advance. So if I'm a cloud provider, I need to support you with your spikes as well. I need to be able to predict that. That's part of the SLA. Otherwise, I'm breaking my service agreement with you because I cannot support that. So in cloud computing, the service performance will not be measured by the average speed, but the consistency of the speed, right? It's different terminology used. And it's not just capacity cost, right? I need to buy more hardware to support that. Operational goes together. DevOps, right? The ops side of the house, it goes together. So if you look at modeling performance, how we basically use that. So as I mentioned earlier, we need to model the performance. We need to be able to deal with the spikes and valleys over time. And this means we need more accuracy models for performance and fast capacity. This is an example from a site called Cloud Harmony. It's an online benchmark tool available for you to use. It's actually a very cool tool because it allows you to benchmark external providers. Here I listed Amazon, Azure, Google, and Rackspace that actually runs on top of OpenStack. And you can actually go and do predefined settings. Here I actually choose disk IOPS. What I do, if you connect that to what I said earlier regarding history, if I need to now put my business in a cloud provider, I can actually check the credibility of that service provider over time when it comes to IOPS, networking, capacity, et cetera. And of course, I can even create application models for that benchmark. So if we look at the deterministic concepts and goals, capacity planning in the cloud is much more like 2048 game than Tetris, right? You cannot just have this capacity fall on top of you and expect everything will be okay. It doesn't work that in a cloud model. So performance consistency is a big part of it to enable us to scale. And how do we achieve this determinism with OpenStack? That's our next piece. Now that we understand why we need capacity planning. So back to you, Keith.
So OpenStack has these three areas of concern: compute, networking, and storage. So we're going to break down each one of these and what it means to actually build a cloud that's deterministic. So up next is compute. So here are the resources that are in contention when you size or plan for a compute node in your cloud. So you've got CPU resources, you've got memory limits, and you've got disk limits. Disk in this case would mean ephemeral disk, local to the VMs. So all of these make up a compute instance family. So how do these guys do this in the public cloud? Well, if you look at Google, which is on the left, and you look at Amazon, which is on the right, there's this concept of fractional proportions. So if you look at the very top, you'll see a virtual machine that's extra large, right? The next machine down, which is large, is actually 1/2 the capacity of the one above it. The next one down, medium, 1/2 of large. Next one down, small, is 1/2 of medium, okay? So what does this gain us? And why do these guys do this, all right? The thing here is that when you take this approach, you get very clean capabilities for scheduling and bin packing. So if you see here with the Russian dolls, if you solve for the extra large use case, you automatically get the other virtual machines in the instance family by default, okay? So what does this look like in terms of a compute node? Well, if you have a compute node of certain ratio of resources, let's say 128 gigs of RAM, 16 1 terabyte disks, and 2 processors, right? Well, if you define that as your general compute instance family, then you can efficiently bin pack those virtual machine types into that node, okay? So going back to the difference in the requests, you as an Elastic Cloud provider, using something like OpenStack, this is the menu that you present to your tenants. You say to your tenant, hey, this could be general compute .small, large, extra large, et cetera. And this is what you provide to your tenants. And then what you would do is, for the different resources of contention, you'd have a compute node that was configured to solve for compute optimization, okay? And if you look at the top, you'll see that Google and Amazon do this today. So on the CPU optimized instance family on the right, you'll see N1 high CPU, right? So when you request a virtual machine in that instance family, it's going to get placed on a hardware node that matches that configuration precisely, okay? Same thing with memory optimization. So in a memory optimized node, you can think about it, this node is going to have more RAM than one of the other nodes. So when you request an N1 high mem, or on the Amazon, maybe an M2 or CR1 class of virtual machine, it's going to be placed on a compute node that matches that profile. Okay? This is how these guys provide consistency of performance at very large scale. They don't let the customer randomly just create a virtual machine and plop it somewhere on a node. Okay? And finally, on the left there, you have a general compute node that kind of solves across the board for all three. So we created a calculator to help you size these things. We're actually going to go through a demo. This is the output from the calculator. And the goal here is to have very flat tops so that you're not bound or constrained by one particular resource over another. So the calculator will visually show this, and it will allow you to do what's called a custom instance family. So we have a lot of customers in the federal services space, and they're kind of spoiled because they have a lot of money to throw at IT, and you've got developers that require a 64 gig virtual machine, right? So the reason I bring that up is that if your organization is used to a certain set of requirements for a virtual machine, you can actually work backwards, define your resource class, your instance family, and then offer that to your developers, but also have hardware that matches that particular use case very nicely. So let's actually look through the tool. And we're going to release this today. It's going to be on GitHub. There'll be a URL, and you can download and you can play with this. So this graph matches the one we saw previously, where we're solving for the general compute instance family. So if you look here, you'll see N1 standard, and you'll see Amazon's M1 class. This is general compute. So I'm going to do 2 quick examples here. You can play with this later. So we have customers that say to us all the time, well, what kind of hardware should I use for the cloud? Okay, then we go back and ask the question, what kind of applications do you tend to run? Are you trying to repatriate existing public cloud instances and trying to get service fidelity with Amazon or Google? If that's the case, then you can go with something that we've already predefined, right? Which is going to translate into a machine node, a machine configuration. But we have some customers that they say, well, I'm just going to put as much RAM in the box as possible with disks and such. So we're going to change the memory from 128 gigs of RAM to 256 gigs of RAM. Okay? So based on this target instance family of solving for Google or solving for Amazon, you can see at the bottom here in the graph, you've got 3 bars per VM. So one is by memory, by ECU, which is CPU, or by disk. And you can see that even though you can pack more machines, virtual machines, into that node by memory, since you increased the memory, you're still going to be resource constrained by the amount of disk on the box, the ephemeral disk. You're still going to be resource constrained by the amount of CPU in the box. So you want those tops to be very flat, okay? And then some people will say, okay, I don't want to put 16 disks in the box. Maybe I only put 8 disks in the box. And then you can see now you're constrained by disk. So you're only going to be able to put so many virtual machines on that machine by disk, right? So we'll back out these changes. So you want something that's even. You want the numbers to be fairly even across the board so that you get very efficient bin packing of those nodes. Okay, so next up will be Tushar talking about storage.
Thank you, Keith. Again, I'm Tushar Katarki. So we talked about how to do capacity planning in why is it important, and we talked about in compute how to do it. So I'm going to next cover how to do it in storage. Case of storage is the clicker. So as you know, we've been talking about it. Again, as the case was with compute, with storage also, you can optimize for various, there are various trade-offs. You can optimize for general storage, which is generally capacity. That's what you're optimizing for, capacity and cost. Or you can optimize for IOPS and latency, or you can optimize for throughput. And we're going to talk about each one of these next. So just before we get there, we're going to talk about what do a couple of popular public cloud providers provide today. So we look at Amazon and we look at Google Cloud Platform. If you look at Amazon, they offer two basic storage options for you. One is on the left, which is the capacity optimized. This is for your general purpose workloads. There are no IOPS guarantees there. They charge per gigabyte and also per million requests. And so you're basically billed by size and IO usage. Whereas if you look at they have something called the provisioned IOPS tier. That one is actually made of SSDs. The SLA guarantee there is IOPS and latency response. And this is what they recommend for workloads which have very high IOPS requirements. And there, they actually bill you for provisioned IOPS. If you requested for 1,000 IOPS, they'll basically bill you for 1,000 IOPS per month, you know, and for obviously the amount of storage. So this is what Amazon does, right? Now, if you look at Google, it kind of does a blended approach, wherein it is basically saying that, you know, you can request. Let's say if you want 100 gig, you can request 100 gig. For 100 gig, I can guarantee you certain SLAs, IOPS SLAs and throughput SLAs, right? And if you really need more, let's say you want, instead of 100 gig, if you want, if you want more IOPS performance or throughput, then you simply ask for more storage. So if you ask for 100, let's say you get 1,000 IOPS. If you want 2,000 IOPS, then you ask for 200 gig. So that's the blended approach. So ultimately, what you can do, you can do something similar with OpenStack. And obviously, OpenStack are private clouds, so you have much more flexibility here. And you might want to do something which actually suits your enterprise and your workload. But this is just to give you one example of how you could think about it. On the left side, as you can see, on the left side, we have the performance optimized tier, in which is made up of all SSDs. Whereas on the rightmost side, we have the general storage tier, which is all optimized for cost and capacity. And then in the middle, we have the throughput optimized storage tier. As you can see, on the left side with the SSDs, it's all about IOPS performance. That's the metric. That's the SLA that you are guaranteeing. In the middle, for a throughput optimized storage node, it's made up of fast SAS drives, for instance, could be the way to do it. It's throughput tuned for the network, both internal and external, is tuned to get the maximum throughput that you need. And so it can be, that's your throughput optimized tier. And then finally, like I said, on the right hand, on the general compute, all you care about is how can I pack as much storage as I want on this. And this is mostly your your general purpose storage. So this is just one example of how to do it. And in the case of OpenStack, the way to do it is Cinder, right? I mean, Cinder filters and schedulers is the way to do it. So it's a 3-step process, as you can see here. The first one really is you basically, as an operator, you choose what are the various storage backends that you want. So in this example, we say you have a IOPS performance tier, you have a throughput tier, and then you have your general purpose capacity tier. Next, you create the volume types, as I've shown here as an example, general performance and throughput. This is what the operator does. And then the tenant or the user goes and creates a volume and creates, here we actually have an API here, Cinder create. You specify the volume type. They want a IOPS optimized type, and they specify the size, and voila, you get a volume of, which is actually, the Cinder basically what it does is that it actually filters the hosts for that particular type of IOPS, so which is the blue tier here, or the IOPS tier, and it creates that volume on that particular tier. So that's just one example of how you could do that. So the next slide actually, so now we talk about the capacity. Now we talked about the 3 tiers. We talk here about how to do, if you have a capacity optimized tier, how do you do capacity planning? And the idea really here, when you think about just a capacity planning, is to think about raw capacity of the storage that you need, and you go to account for replication, something like Red Hat storage or Gluster. You have a replication factor, and then the RAID type that you use. So I mean, different RAID types offer different. So the table actually is a ratio of total usable capacity to total capacity to usable capacity. And you can see as the RAID for RAID 5 it's 2.2, for RAID 6 it's 2.4 because you have 2 parity bits, and then for RAID 1.0, since you mirror, the ratio is actually 4. In other words, so and then you got to consider the amount of replication that you want to do. If it's 2-way replication, then obviously it's double. It's 2 times whatever the RAID 5, RAID 6, and RAID 10 ratio is, and with 3-way, it's 3 times. And then, so here's a calculation. If you want 12 1 terabyte disks configured for RAID 6 and 2-way replication, then what you do is that you do 12 terabytes divided by 2.4. That gives you the 5 terabyte net capacity, and that's what you would use. If you need 100 terabytes, then you would basically divide 100 by 5. That is 20 servers is what you would need. So that's the way to calculate capacity. On the performance side, if it's a performance optimized tier, you basically, in this example, I have shown actual Red Hat storage performance that our performance guys have done. There's a separate talk on that, but here is the write performance, here's the read performance for IOPS. And the 2 things that you've got to keep in mind here really is that IOPS scales linearly, but at some point it's going to start tapering, as you can see, because there are just too many, the disk is spending too much time just doing seeks. And the other thing is latency, the latency response. So depending on the SLAs that you want to offer, you can choose what your per storage node IOPS performance is, and then based on that, you can decide, if you know how much workload you expect, you can decide how many servers or storage servers that you will need. Similarly, for the throughput optimized case, we talk about a similar calculation can be done. Again, this is just a graph of Red Hat storage throughput performance for sequential I/O workloads. On the previous slide, it was about random I/O. Here we do sequential I/O, and there you can see that there is a separate read. And 2 things that you got to matter here are, you'll see that there is the throughput actually. The read and the write throughput is completely different, and that's because that is influenced by the RAID type. So you might have to consider that, as well as the read-write mix of your workload in calculating this. So with that, so I want to bring it all together. So what does storage capacity planning in a private cloud with OpenStack means? You got to think about what your storage offering is. I mean, you can either offer capacity-based, performance-based, or throughput-based, or you could have a blended approach like Google is doing. The second step is what storage tiers do I need depending on that. You've got to decide that. Then you do need storage capacity planning. We show some examples of how you could think about storage capacity planning. And then you obviously procure and deploy, and then you use something like Cinder Scheduler to actually steer the workloads or incoming volume requests to the right storage tier. With that, I'll hand it back to Keith.
Okay, so the last area of determinism here is based on networking, and it's probably the most critical when it comes to OpenStack, if you're going to be successful with OpenStack. So the contention here with networking is based on these three areas. So you've got resiliency, meaning that if a switch fails, your cloud doesn't drop. Latency, which means equidistance between nodes within the network, regardless of scale. And then throughput, making sure that, for example, if you have a block storage node or a rack of nodes, that the throughput for that is taken care of, which may look different from general compute. So there's network oversubscription ratios and things that we can discuss there. So we'll jump right into this. So on the left is a traditional enterprise topology. This was taken from the VMware CTO blog. Very good example, but it was related to Hadoop. Hadoop and OpenStack have very similar use cases in terms of not just north-south traffic optimization, but east-west traffic optimization. So we talk to customers on a day-to-day basis, and most folks are trapped in the 90s when it comes to networking. They think that this whole top-of-rack switch aggregation core model is the standard one that they want to use going forward for something like OpenStack, and is absolutely the thing that will kill you in OpenStack, okay? So we need to move to something more cloud-friendly, more modern, which is a network topology that gives us uniform bandwidth throughout the entire data center. And it's based primarily on a span and leaf topology. There was a guy, I don't want to date myself, but before electronic switching took place, ESS4 and ESS5 from the Bell days, there was a technology called crossbar. And crossbar technology was similar to this, but it was not electronic. If you want to do some research, look up Klaus Fabrics, C-L-O-S, and you'll see some of the early thinking and philosophy with Klaus Fabrics now transcended to cloud here with the span and leaf topology. So why is elasticity required? Well, if you look at the screen here, this is a logical representation of your elastic cloud. So you can just pick a color and assign it to any given resource in the cloud. So maybe the dark squares here are SSD-based block storage, right? Okay. Maybe the light blue is general compute. The point is, each one of these things here in the cloud, where this guy, no matter where he is within the network, should have equidistance access to some other node in the network. Okay, that's the takeaway here. So this connection, the connection or the latency between these two nodes anywhere in the cloud should be the same as maybe a node that's in the same rack, okay? I mean, we're not gonna get it perfect, but it should be damn close. So the cloud will grow. So what we saw on the previous slide was your beginning OpenStack, right? And now the DevOps gurus are taking over and they want more, and you have to accommodate that. So you have to have a network topology that's going to scale almost as elastic as the tenants are expecting to consume those resources, right? So the question here is each one of these boxes, is it a compute node, or is it a resource node, compute, storage, whatever, or is it a rack? Okay, each one of those boxes could be a rack, and then how many nodes are in that rack? 16 nodes per rack, 32 nodes? Well, if you build your network topology correctly, the answer is it doesn't matter, okay? Because no matter the size, you can, I mean, there's some nuances, obviously, when you grow, but it should scale nicely and provide that uniform bandwidth throughout the entire cloud. Okay, so from an OpenStack point of view, the things that we care about are availability and resiliency. This is absolutely critical because of things coming down the pike like SDN, right? So in this network topology, in a span and leaf topology, you want to lay out and define a completely routed layer 3 core network, right? Because that gives us the ability to come back on top of that with a software-defined layer 2 network that's for your tenants to use, so that one virtual machine can use SDN-based L2 connectivity over top of your layer 3 core to talk to the VMs. Again, network latency is a big deal, and we want to be able to manage congestion based on the type of resource that we have under management. So again, block storage with SSDs will require high throughput. So you'll configure your top-of-rack switch and all the nodes below it a little bit differently than you would do a traditional compute node. So a spine and leaf topology is pretty much the way to do this, okay? So there's a lot of documentation out there to do this. This is from Brad Hetland's blog using the Dell Force 10 switch family. Very, very powerful features. This can grow to basically, if you look at the bottom there, it's 1,280 10 gig interfaces. So if you assign one server to that interface, that's 1,280 nodes in your cloud with uniform connectivity between each node. Okay, so we talked about compute. Well, first of all, we talked about a cat on a unicorn, okay, number one. So that's the demand, this whole DevOps application infrastructure as code pressure, right? So that's given. So we talked about OpenStack. We talked about compute, how to size that, make it deterministic so you can get consistency. We talked about storage, and we just talked about networking. All right, so what we're gonna talk about now is how do we bring all this together to get the master plan to do OpenStack properly. All right, so remember this guy, okay? This is the guy we're solving for. So this is the theory that we're trying to get here. So we have our core fabric. That's the first thing you want to lay down, right? The spine and leaf topology, top-of-rack switches. I have a scale background, so when I think of a resource, I think of a complete rack dedicated to that particular resource, right? So we have compute and storage, which is obvious. And then we have OpenStack is kind of the glue tying everything together in terms of scheduling. So when a request for a particular volume comes in, the Cinder scheduling service will place that on the proper node. We have a request for a high memory virtual machine instance. It's going to get placed on the proper node within the network. Okay, so this is the binding. What you walk away from is a resource level that's consistent for the cat on the unicorn, okay, for your tenant. So you always want to make sure that the marriage of all three of these things is in harmony, and this is the sweet spot for the Elastic Cloud. All right, so what does this look like in more practical level? All right, so again, this is our target here in terms of philosophy. But this is a very high-level network architecture that's specific, that's for OpenStack, okay? So let's actually break this down into three areas, following this model. At the top, we have the spine and leaf topology. So we have core switches, we have top-of-rack switches, we have edge switches. Again, the benefits of the spine and leaf topology give us the resiliency we need, where you can drop out a core switch and everything still runs, okay, number one. And then the second piece, where you see OpenStack as a cloud controller, we've dedicated a rack on the left for all the OpenStack services. So Horizon, Keystone, Nova Scheduler, Cinder Scheduler, all the core pieces that you need to run OpenStack are presented here on the left. And then we just arbitrarily picked resources that we're going to bring into the cloud. So we've got general compute, which is that M1 class, right, for compute nodes. So each one of those nodes in that rack will be configured to support the request for an M1 virtual machine, so we can get that efficient bin packing on each one of those nodes in the cloud, okay? And then performance storage, this might be a rack of SSD boxes. General storage, this could be, deep and wide, SATA-based drives in those boxes, kind of general storage, right? And because they're deterministic as a separate failure domain, we can now just scale this out on demand as we need to. So if you are looking at your OpenStack cloud and you see that you're at 80% capacity for M1 as a family of instances, then you need to know that, well, you know that you need to bring in maybe another rack of gear to support that instance family, okay? So we'll take any questions that we have now. There's a separate page that shows resources. The What is DevOps ebook is a free ebook listed here. And the GitHub URL for the calculator is right there. Sorry about the resource 3 thing. If there's any questions, we'll be happy to take them at this time. Oh, sorry, guys. Yes, sir. There could be. I've seen OpenStack cases where there is a separate storage network. The reason, though, was for enhanced security, breaking out a separate security domain for storage. But in most of the use cases that I've seen, the compute nodes are dual NIT, 10 gig E bonded into your fabric. And then the storage NICs are pretty much the same way. And you do your traffic over that network. Yes. Oh, this one?
Yeah. Now, if you go back to the very first picture you showed between enterprise network and cloud network,
Yes.
this looks the same as the enterprise. I mean, you have your edge switches, your core, and your top rack. It's very similar.
Yeah. No, I get your question. So it does look similar, but it's not. Because we have non-blocking I/O. If you follow the packet, so to speak, you will have non-blocking I/O at wire speed throughout any of this network. And there's no, so for example, there's no, no, it's just a standard switch. Yeah, there's nothing magical. It's just a different approach. Let me see if I can find that original. It's at the beginning. No, networking. Come on. This guy. So at the core, where you have the connectivity, so you're going up the tree and then back down the tree, right? If every single host at the bottom left, this is typically a layer 2 scenario. Yes, that's the takeaway here. This is typically layer 2. So you could actually, if every single host decided to send data up, you could saturate those networks and you wouldn't be, you've reduced to whatever the connectivity is between the core. This is totally uniform throughout the entire the network, yeah. Yes. And the last thing I'll say about that, or another thing I'll say, is that this scales nicely. This is really bound by the port density of your switch. So if these are 48 port switches, which is why you got that 1280 count from the Dell picture. If you exceed that, you can actually do what's called a substage or multi-staging spine and leaf, where you actually break down one more level, and then it's like you can do a complete availability zone with like 18 to 40,000 servers. It's ridiculous. And the uniformity pretty much stays the same throughout. In the Dell example, they were saying that it's like, I want to say 8 microseconds from one node to the next within the spine and leaf topology. Yes, sir. It would be at the edge here. Yes, all the edge. So for customers, we would say, hey, look, the edge point is where you start to interface with OpenStack. And we've seen cases where, so in the business sense, there are a lot of customers who started out using Amazon. And then what happens is the cloud bill gets bigger and bigger and bigger every month, right? So once you get to about $25,000 a month with Amazon, it starts to make sense to look at doing something like this at a colo facility, especially one that has Amazon Direct Connect. Because now you can have a set amount of hardware to run, let's say 80% of your workload, and then you can use Amazon Direct Connect to burst out to get the extra capacity that you need. And that edge demarc there is where you could bring in the connectivity for Amazon Direct Connect. One last thing I want to show, which I skipped over pretty fast. So here, when you define your hardware type and you give it resources, when you use the calculator, you can determine the maximum number of virtual machines that would fit comfortably inside a compute node. So in this case, if we were solving for Google or solving for Amazon, you'll see at the bottom at Amazon, because their instances are smaller in terms of resources, you can put 64 virtual machines on this box. So, okay, so big deal, right? The point is, this gives you some insight into the amount of IP addresses that you're going to need for your tenants in terms of elastic IPs. So this machine, 64 IP addresses maybe, times 16 machines in a rack, times X number of racks, and then you say, okay, I need this much in terms of routable edge elastic IP space. So that's another point of helping you to plan your cloud as well. Oh, yes, sorry. Yes. The services related to, oh, for the core services that were on the, yeah, so those are just standard OpenStack services. So if we go back to, let's go here. So if you look at this, right? So there's Keystone, there's Nova, Neutron, Glance, Cinder. These are all the services, basically OpenStack software that needs to run somewhere. This is the command and control for your cloud. Yeah, and we put all the OpenStack services in that particular rack. Yep. Sorry? Yeah, that's the, that's a good question. So when the guy at the top requested a virtual machine, so Nova has a component called the Nova Scheduler. So the request comes into the scheduler. I say, okay, I need to find, based on my filters and my rules, what compute node that we're going to select to render this virtual machine. So this tag your it means that it's went through its rules process and came out with a compute node, and boom, you're going to be the one that we're going to render to. Okay. Yep. Any last questions? Yeah, it's not a label. It's not an attribute tag. Yeah. Yes, sir.
Yes, so Keith actually mentioned the Cinder Scheduler, and Tushar actually mentioned the volume types. And this did actually happen. Just like Nova has a scheduler, Cinder has a scheduler too. And for us to provide quality of service in OpenStack, we basically look at the spec of the driver. So if I have a backend that Keith mentioned solid state, for example, I want to create a performance tier for solid state, I need to be able to utilize the driver specs. And what Cinder does is actually look at the specs to route, of course, to the relevant backend. But what we can also do in OpenStack is that different backend providers that does provide quality of service in the driver level. So because it's a marriage, right? You need two parties for that. And a lot of companies, such as SolidFire, et cetera, can provide that driver today. So what they do is there's an extra spec in the driver that Cinder Scheduler can actually look at and be able to utilize the quality of services. So I can actually get a guaranteed IOPS tier, right? If you recall back to the earlier talk when we actually showed the usage, right? The end goal is basically to provide different choices up to the user. So I can create a custom menu just for different levels of quality of service for storage based on that. And what happens is that OpenStack basically delivers that all the way down to the driver based on the scheduler. Right? Can you go to the last slide? I think we have resources as well. Yeah, so the previous one is basically the tool, which is free. And we also put together here some open source tools that allows you to do monitoring and benchmark. These tools, the two open source monitoring tools are actually within OpenStack. So if you download the presentation, just click on them. You'll go to the relevant OpenStack links. The benchmark tool I mentioned is the Cloud Harmony that allows you actually to benchmark different cloud providers externally, different characteristics, disk IOPS, network latency, et cetera. It's very beneficial to look at the history as well to identify what's going on and use that for capacity planning. All right? So we'd like to thank you all. Thanks.